We're going to talk about actually force field parameters for classical MD simulations of biomolecules. So we are not going to cover all sorts of force field parameters for materials and other things. We just concentrate on biomolecules, which is the focus of this workshop. And so oftentimes this might actually become a sort of very critical step for you, because again, for a standard amino acids, nucleic acids, or bases, or nucleotides, lipids, water, ions, you have a standard force field. People have done this for you, but then you might have a drug or a modified residue or a post-translationally modified kind of part of the protein, or two residues fuse into each other. So something special in the protein that is quite common, actually. You might want to phosphorylate a residue or things of that sort, and then you end up with a different molecular species for which you don't have any parameters. And if you don't know where to get to start, then that's the end of the project. Okay, I cannot do MD simulation for this. So this has become such a common problem that we decided actually to focus a little bit more on this. We even actually dedicate the whole day talking about force field, how they are made, where they come from, where they are stored in the files. And then we even actually developed a sort of program that can help you to go through the sort of tedious steps and the process to simplify the steps of setting up all the calculations that are necessary to do force field parameterization, and to analyze them, and to collect the data, and to do the fitting and everything, all the steps involved. Still, you need to know what are the steps, but the tool that we will talk about helps you go through these steps much, much easier. Parsing all the output files, getting all the information, sorting them, et cetera, et cetera. But OK, so then at the same time, I don't want to just talk about a very tedious process today. So I try to use some examples, some practical sort of examples that might be useful for you guys when you are setting up your simulations and calculations while we are looking at these details. OK, so yeah, so we are going to look at some of the files that you are using for your NAMD simulations. Charm simulations are pretty similar. In Amber, GROMACS, they might be in different places, but essentially you need this kind of information before being able to run the simulation. So we talk about topology and structure files. These are the topology file, the PSF file that you generated, in which you have the topology information, connectivity, how many bonds you have, how many angles, dihedrals, where are the charges, et cetera, et cetera. Parameter files, we're going to open one of these files and look into the parameter file and see what's in there. If you want to modify something, if you want to add something to it, where to find this information, so that you feel more comfortable doing that. If you don't know where this information is, then you probably avoid. That's a big initial barrier usually. Where all the numbers that are needed by an MD engine, NAMD, Charm, Amber, whatever, come from. Where to find these numbers and how to change them if you need them, how to make topology files. That's actually one of the tutorials you can go through this afternoon, how to create a new topology file. There's an example you go through. And then for ligands that you have, for drugs, cofactors, special amino acids, and then how to develop and put together missing parameters. That is probably the most difficult step. Yesterday, we talked about this example. So when you are doing classical MD, you treat these particles, these atoms in our case, because we are dealing with molecules, at points in a space with the specified coordinates. And then you have initial velocities for each of them, either randomly assigned or coming from the previous step of your simulation. So you have initial positions and initial velocities. And then the only thing that you need to do is to calculate how much force is acting on each atom, and based on that force, calculate acceleration, change the velocities, position, et cetera, and you just propagate this into the system. So the only thing we need to do is to define the forces. We started with van der Waals forces, or And the forces are vectors. It's easier to talk about potential energy, the derivative of which would be the forces. So we have the general universal van der Waals interaction coming from induced dipole interactions between atoms. You know, electrons polarize instantaneously here. You get a little dipole here that induces a dipole in the neighboring atom, and that results in some sort of attraction. So that's the origin of the attraction between any two atoms, any two electronic clouds coming close to each other. But then when you bring them too close to each other, they start repelling each other. So that's the positive part of this Lennard-Jones potential that we use to represent van der Waals interaction and non-bonded interactions in any pairs of atoms. So some parameters are involved here, epsilon, ij. I is atom 1, j is atom 2. The distance between them comes from your simulation system. The program can measure this distance for you, knows that. So you have to specify epsilon ij, how deep the interaction potential is, what's the strength of interaction, and then R min ij would be the optimal distance at which they have the minimum energy configuration. Two parameters should come in here, and we have to give these parameters to the program. Otherwise, it cannot calculate the energy and the forces and things of that sort. Another type of non-bonded interaction, so this was very universal non-bonded interaction existing between any pairs of atoms. So as you will see, it would be very, sort of looks simple, but then if you look at it, in principle, it exists between any pairs of atoms. And if you want to do it for the entire system, you are dealing with an n squared number of terms to calculate. So if you have n atoms in the system, everything is interacting with everything else, it becomes n squared problem. So that's why oftentimes we say, okay, well, I mean, this term is dying, r to the 12, this is dying with r to the 6. So they are dying very quickly. They are short-range interaction. We don't have to go 15 angstrom, 20 angstroms away. We're going to define a cutoff and say for every atom, I'm going to go only 10 angstrom or 12 angstrom or whatever the force field has been optimized for. So we define a cutoff distance, and only within the cutoff distance we are going to calculate these short-range interactions. That requires for the program to update the neighboring list because things are moving. At this instance, you might have 10 neighbors, but then 5 picoseconds later, you might have 15 because atoms are moving, coming in, going out. So that's a little bit of extra work for the program to update the neighboring list, but it does it at 20 or 30 or so time steps, not every time step, because they're not going to move too much in a few femtoseconds. So it's not necessary to update this every time step. OK, so that's one type. And now we have another type of non-bonded interaction, electrostatic interactions. If you have charges, if you don't deal with neutral particles, then the charges can attract or repel each other. And again, we have to specify these what we call partial atomic charges. Such a concept doesn't exist if you talk to quantum chemists, but we have to do that. We have to assign a charge to this atom because we need to calculate some sort of electrostatic interactions. We need to have some sort of electrostatic representation between these two atoms. And the only way we can do it right now is to say, OK, this guy has a fixed charge of 0.5, and this guy has a fixed charge of minus 0.5. Here's the interaction. And then when you assign these charges, and that's actually one of the most important parts of parameterization, because that's the strongest kind of non-bonded interaction you have when you're looking at the ligand-protein interaction or a drug binding or something like that. These are usually you're dealing with non-bonded interactions between two species in the system, and charges, electrostatic interactions, are the strongest type of forces that you have. So assigning good charges is a big deal and very important step. OK, so the distance comes from the simulation, the configuration you have, PDB or the previous step of the simulation, but we have to assign the charge, partial atomic charges for the two atoms. So these are non-bonded interactions, so pretty simple and easy. You will see not too difficult to define them when you want to set up a molecular simulation. The difficult part is that takes a lot of time and lots of files and lots of lines in the file is the topology of the system. So you are dealing with a molecular system again. Some of these atoms are connected through bonds or bond angles or dihedral angles for which we have explicit terms and explicit rules, different rules to define how they should treat each other and act on each other. But then in addition to that, if you have atoms that are too far apart, like more than 3 atoms apart, for example, this guy and this guy can, through a space, have non-bonded interactions, or this one and this one, for example. There is no chemical bond connecting them, and they're not going to go beyond 3 bonds. 3 bonds would be the definition of a dihedral angle. Anything beyond 3 bonds, we treat them as non-bonded pairs in our treatment. So now we have to specify what is connected to what, how many bonds we have for this atom in the center, what kind of atom it is, how large it is, what would be the bond distance optimal for this bond. So you need to have atom types for each of these, and then you need to have parameters describing that bond, the mechanics of that bond. So I mean, what's the equilibrium distance and what's the force constant, because we treat these bonds as springs, for example, et cetera, et cetera. So the type of bonded, some of the, most common bonded interactions that we have, at least for biomolecular simulations, are, I would say, bonds, bond angles, and dihedral angles. These 3 are the most fundamental ones. Every force field has them. So these are treated as springs. You need to specify spring constant and equilibrium bond distance. We have bond angles. Again, we treat them as harmonic potentials. So you have an equilibrium value, the minimum energy value for that bond, and then you have a spring constant determining how the bending motion is. Usually these are softer, lower frequency degrees of freedom or vibrational modes compared to bond distances. They are bond distances, bond length, or bond stretching is the stiffest degree of freedom, the highest frequency of motion you have in the molecular system. Then we have dihedral angles. These are extremely important for very large conformational changes in proteins. It's all about dihedral angles. Secondary structures depend on the dihedral angles of the backbone. What the difference between a helix and a beta sheet is all about dihedral angles. So these are very important for conformational sampling. So composed of 4 atoms, and we'll see they are treated using cosine function, a periodic function allowing the free rotation of this bond. So let's call these proper dihedral angles because you have 4 atoms in a row, and you define 2 planes, and the angle between the 2 planes would be your dihedral 2-plane angle. But you can also have improper dihedral angles, or in short, improper angles that can be defined for a center. And as I think I mentioned yesterday, you can use that to impose a particular geometry to that center. Keep it planar. We use this a lot for sp2 centers, for carbonyl groups, for example, for peptide bonds. If you have also an sp2 center in the side chain, you will see there are improper angles there. Or you can keep it a pyramid in a pyramidal shape, as shown here, by imposing this. And again, the goal is by a right combination and mix of these bonded terms in my potential energy, I would like to be able to reproduce the molecular structure and dynamics of these molecular systems. That's the idea. I know a lot about this from vibrational spectroscopy. There is a lot of information coming from vibrational spectroscopy telling you what's the bond distance, what's the frequency of vibration here. I have idea about the mass of these things, so I can tune my force field to be able to reproduce the molecular behavior. So before I go on, so one thing to remember is that, and one strategy is in force field parameterization, is that we always use small model compounds and then develop our parameters for a small molecule, let's say this guy, and then we use those fragment parameters and hope that they are still valid if you use them in the entire protein. So nobody develops parameters for the entire sort of peptide or entire nucleic acid or anything. Or even if you have drugs, don't try to develop parameters for the entire, I don't know how large it might be, maybe 100 carbons in your system, thinking that, oh, this is the best representation I have for my molecular system. Try to break it into isolated chemical groups and fragments, develop parameters for those fragments, and then put them together, because that's what has been done for the rest of your simulation, for the protein, for the lipids, everything. So we start with model compounds. We have a lot of physical chemistry information about these model compounds. If you want to know, I don't know, heat of vaporization for your protein, probably you cannot find it, but you can easily find it for small molecules that exist in your protein, and try to tune your force field with those experimental data, and then try to hopefully use the same parameter set for your larger molecular system. So the idea of transferability, starting from model compounds, small model compounds, and being able to apply it to larger molecular system is fundamental here, so you don't have to put too much effort for your own drug molecule to put everything in one Gaussian calculation, because you think this could be the best. So you will see this again and again today. Okay, so that's, again, I think we looked at this yesterday. So that's a typical example of a biomolecular force field or potential energy function as a function of coordinates. So we have to define all the bonds in the system. The NAMD doesn't know what is connected to what. You have to say, there is a bond between atom 2 and atom 5. OK, so there is a bond there. Now give me the force constant for that bond and equilibrium value for that bond, because that's how I calculate the energy and the force and everything. All right, so we have to define all the angles. And for each angle, we need to have a force constant and an equilibrium value. For dihedral angles, we have to define them, tell the program how many dihedrals we have between what set of atoms. And then for each dihedral angle, we need to have a constant here specifying the barrier against the rotation of that bond. And then we need to have the periodicity. Is it a methyl group? Every 120 degrees, you will have the same configuration, 3 minima and 3 maxima during one full 2-pi rotation. And what is the location of the minima and maxima? What is the phase? So 3 parameters for each dihedral angle needs to be specified. So these are the bonded terms. I don't have the improper term included in this example, just to give you some ideas that we need a lot of parameters. And these are the non-bonded parts of the potential energy function. Again, we need partial atomic charges, and we need to have, you saw R mean specified in my previous example. Sometimes you see this specified as sigma, which is essentially representing the size, the radius of your atom here. And we need to have epsilon ij, how strong the interactions are. OK, well, this is supposed to play, show you the bond vibration here, this bond stretching motion described by a harmonic potential, also showing the bending of these carboxy groups. I have to animate it myself. So described by a harmonic potential, and then rotation of this methyl group, which is described by this cosine function. So just as an example, let's say we have CC bonds in your molecular system. So this CC bond vibrating, so the only way to tell the program whether it's a single bond or a double bond or a triple bond is to specify different types of force constant and equilibrium value. So we say we assign different atom types to these carbon groups. We call them, for example, I don't know, CT3 and CT3, CT2, CT2, CT1, CT1. And those atom types will use different sets of parameters. For example, for a single bond, the atom types will use a force constant 100 kilocalorie per mole per angstrom squared. That would be this shallow potential here, and a longer equilibrium value at 1.5 angstrom. So this blue curve would be describing the vibration of a single bond. When you go to a double bond, it becomes shorter, moving a little bit to the left, the purple curve here. And then the force constant is higher, 200 kilocalorie per mole per angstrom, a stiffer spring, so which means a higher frequency motion, and also a sort of rise in your potential energy is much larger as you deviate from the minimum energy configuration. And for a triple bond, this is a triple bond on my screen, and it's going to be even shorter bond length and higher force constant. So that's it. That's how you distinguish between a single bond and a double bond and triple bond. So you don't have to do anything else. The program just need to know that it's shorter and it's stiffer. That's it. And it's all done by using different atom types. So bond stretching, as I pointed out, is the sort of highest frequency motion and very stiff. So these are the largest kind of force constants that you see in the parameter file that you use on the order of hundreds of kilocalorie per mole per angstrom squared. And these are, again, as we know that from vibrational spectroscopy. We talked about the CH bonds being the highest frequency degrees of freedom in a molecular system because the hydrogen has a very, very small mass. In the denominator, the frequency is going to go high, and therefore those are really our limiting factors in terms of the time step. If you can somehow confine them, restrain them, or get rid of the hydrogens in our molecular system, then you can take longer time steps, as we discussed yesterday. So bond angles would be similar harmonic potentials and quadratic functions to describe them, but their force constants are one order of magnitude lower, in the order of 30, 40, 50 kilocalorie per mole per radian squared in that case. So after degrees of freedom and take longer periods to take place. Dihedral potential, so let's look at an example or three examples of a dihedral potential. So again, three parameters specifying how high the barrier against the rotation of a dihedral angle is. So you see three examples, blue, purple, yellow, going from K equal 10, highest barrier to 5, half barrier, and 2.5 is the yellow. So it's the lowest barrier example that we have here. So that goes into this K here. And then the periodicity specifies how many times you will have a minima and maxima as you go through 2 pi rotation. So this is an example of n equal 1. Purple is an example of n equal 2. Let's say cis-trans bond. I know that in reality they don't rotate, but this would be the proper way of describing their dihedral behavior, because cis and trans conformations are both minimum configuration separated by a barrier. So this barrier can be very high in your potential, let's say 20 kilocalorie per mole, preventing it from happening. And then you have this last example, could be the example of the rotation of a methyl group, 3 minima, 3 maxima, n equal 3, and a low barrier, relatively speaking. So the other thing is the phase. So the phase specifies where is the barrier. The maximum is at 0 degrees or 90 degrees, etc. So you can shift it to. OK. So now, let's now go to non-bonded parameters again. So here we are dealing with van der Waals or Lennard-Jones type part of the potential, repulsion and attraction, and electrostatic. Q of I is partial atomic charges. We're going to have some detailed discussion about that, because again, that's the most important part of the non-bonded interaction. You can specify a dielectric constant here if you don't have explicit representation of your solvent. That's the simplest way of having an implicit representation of solvent. I don't have water. I just specify dielectric constant of 80 here. And that is going to scale my electrostatic interactions the way I want. The problem is, I mean, the dielectric constant is a sort of bulk behavior. Water doesn't always create that kind of dielectric constant. If you have a couple of water molecules in your binding site, it's not going to create a dielectric constant of 80 for you, so that's not correct. You still scale the electrostatic interaction there by this dielectric. Everything will be affected even though you might not have enough water in some places. So that's not a very good representation or way of having the effect of solvent, but that's the simplest way of doing that. So you can specify D in your NAMD configuration file. By default, it's 1 because it assumes that you have everything explicitly present. But you can play with this. You can scale easily your electrostatic charges if you want to test a very artificial system. Yesterday I emphasized this. I do it again. Put the system into extreme conditions and see what happens. That's very nice. And don't be careful, by the way. So I forgot to say this. So you want to say, it's one thing that I have seen happen a lot is that people try to do some sort of changes very carefully. Let's say, for example, you simulate the system at pH 7, and then you want to see if you are able to capture the effect at the lower pH. Instead of, OK, the experiment has been done at pH 6, I'm going to do 6. Go to pH 1, go to very extreme cases, and see if within the limited time scale of your simulation, you're able to see something, even at that extreme condition. If you don't see anything at pH 1, forget about pH 6. You're not going to see anything. You're wasting your time. So go to extreme conditions. You want to see if you capture the effect of temperature. So instead of increasing your temperature 5 degrees or 10 degrees, increases by 100 degrees, and see if the phenomena that you are expecting take place. If it doesn't, at 100 degrees higher temperature, of course, nothing is going to happen at 5 or 10 degrees more. So don't be too careful during the exploration phase. You can easily save a lot of time by putting it in extreme conditions and see what happens. OK, so right. OK, so that's for the electrostatic. So now if we go to the Lennard-Jones part, so we have pairwise interaction. So we have to define these parameters for pairs of atoms. The way it's done is we're going to do, we have this epsilon ij. We are going to define epsilon I and epsilon j for each atom type separately and use the combination rule to have these pairwise parameters. So like epsilon ij would be square root of the product of epsilon I and epsilon j. And then R min ij will be the sum of the minimum radius of atom I and minimum radius of atom j. Sometimes it's the average, depending on the force field, how this is specified. You might see this a little bit different, but the concept is the same. It's the sort of addition of two radii or half radii, depending on how it's defined. OK, so let's see. They have an example. So I don't have an example of this guy. So the shape of your Lennard-Jones potential, if this is 0, so it looks like this. So that's the position here. So what you have, this is R. So this is the position of your R0 or R min, at which you have the minimum energy interaction, and the depth of this is determined by epsilon ij. So at short distances, the repulsive term becomes dominant. So this part becomes dominant because it's R to the 12. this ratio is larger than 1. So you have, at this point, actually, it becomes actually very, very repulsive. They start to bump into each other. At this point, at this distance, r min ij, so you have the minimum energy configuration. That's how they like to sit next to each other. And then beyond that point, they start actually seeing each other less and less, but the interaction is always attractive and negative, right? So that means even at very, very long distances, you still have generally attraction between pairs of atoms. So what does that mean? So that means that in contrast to electrostatic interaction, so electrostatic interaction, you have repulsion, you have attraction, but in the case of van der Waals interaction, at short distances, they repel each other, sure, but at longer distances, which is the case for most of the pairs in your molecular system, everything is attracting everything else. So that means they can add up, even though they are small, and die quickly with r to the 6, the attractive part. Still, they can add up to a large force if you are dealing with large entities. For example, 2 rings. You have 6 carbons here, 6 carbons here. They can actually add up to a lot of van der Waals interaction. 2 membranes, 2 planes. Things can actually, the sort of a bulk number of atoms coming to rather close distances. So the fact that they're always positive actually makes they're always attractive at long distances makes them significant. We are going to cut them at some point because we can't calculate everything. So we're going to define a cutoff and say beyond this point, sort of, let's say 12 angstrom or so, I'm not going to calculate anything. So I'm going to start at 10 angstrom and define a switching function slowly to bring it to 0 at 12, so there is no break in my potential energy, so I can calculate forces consistently and everything. So beyond that, I'm not going to calculate anything, but that could be a source of error in the particular molecular system that you are calculating. Just keep that in mind. And there are efforts in terms of how we might calculate these van der Waals interactions without using a cutoff. So, but the stronger kind of interaction obviously are electrostatic interactions, so they can be repulsive and they can be attractive, and this dies with as a function of 1 over r. So it dies slower compared to van der Waals or Lennard-Jones interactions, but still at longer distances, yes, I mean, it dies slower. Therefore, at longer distances, you still have significant electrostatic interactions between atoms. And that's why people started coming up with ideas and ways of calculating electrostatic forces without truncation. So that was the first concern people had, how we can calculate electrostatic forces without including any truncation, without any cutoff. And methods like PME, particle mesh eval, is an example of how to have actually long-range electrostatic interactions and forces included in the simulations. So charges are important, and now we're going to have some discussion about how charges are done. So again, partial atomic charges don't exist. So there is no such concept in quantum chemistry, but because of the way we have to specify molecular system and calculate the forces, we have to assign partial atomic charges to the molecular system. And again, this is a good example of showing how fragments are used in force field development. So you can start with a fragment. It could be a methyl group. I keep thinking the screen is still low. So I can have hydrogens here, or if you want to do it a little bit better, maybe you can do it like this. So you can design a fragment that looks like that. And this, for this fragment, you can calculate nicely quantum mechanically. So there are really good quantum mechanical levels of theory that can give you nice description of the electronic structure. distribution of charges. Then there are ways of sort of assigning partial atomic charges. You have a density of electrons around the molecular system, and then you can do some sort of population analysis. I will say, I think these electrons, I can assign them to the oxygen. These guys in the middle belong to this carbon, for example. You do some sort of population analysis to assign pieces of electronic cloud to individual nuclei, and you know the charge of the nucleus itself, then you come up with a number for this guy. So that's, for example, Mulliken population analysis is a common way that it exists in many quantum mechanical packages, and you can get easily these partial atomic charges. There are other ways of assignment of partial atomic charges. So what is the point of having these partial atomic charges? So the point is, OK, I want to describe the interaction of this fragment of this chemical group with the environment, right? So now there are two philosophies in the field. One I would call charm here, charm Mulliken, and the other one is Amber ESP. In charm, the idea, Martin Karplus got the Nobel Prize to work on biomolecular simulation. So their idea 30, 35 years ago when they published their first paper, when they were developing this force, the idea was, OK, I need to describe the interaction of this moiety, this carbonyl group of my protein, for example, in the backbone, with its environment. What is the environment? The environment could be another protein side chain. The environment could be water, could be ions. But you cannot have multiple representation of the same chemical group. You need to make up your mind, put one number here. So they decided the most representative representation of the environment would be water. So water is everywhere in biology. So if I fit my interaction with water in my classical force field to some quantum mechanical standard and reference values, then I should have a good partial atomic charge for it. So therefore, they said, OK, so let's place, this is my carbonyl group. I'm going to let me draw it here. So I'm going to do a quantum mechanical calculation. And this is going to form a hydrogen bond with water. So now I'm going to optimize this geometry, calculate what is the optimal bond length and what is the energy of this interaction quantum mechanically. So everything is treated quantum mechanically. So you can get a sort of curve of interaction versus length or distance. And you see, for example, at a particular distance, you have the optimal energy. Beyond that, the energy goes up. Beyond this one, the energy goes up, something like that. So this is the behavior. As to separate the water and this chemical group, this is how your energy changes. That's obviously the optimal distance for you. And this is the energy at that distance, quantum mechanically. So you get these things, QM. And now you want to reproduce this behavior using your molecular mechanic force field, a single point charge assigned to this group, to these atoms. So what you do is now, let's say we start with Mulliken charges. We get them from quantum mechanics. We just calculate this chemical group separately. And then we try to modify these charges, optimize these charges, so that we can get this behavior. In charm, so you fit everything to interaction with water. So therefore, we have to fix one part. Water is treated as tip 3 model, so which has fixed charges like this. That part is fixed. We are not going to touch that. That is the definition of our reference water. And everything else, we're going to work with this guy to fit the potential. So therefore, when you're doing charm calculation, you cannot use any other water models, even though that water model must be better diffusion constant, better dielectric constant. No, you have to use tip 3P. Even though the diffusion of tip 3P is awful, I don't know, it's too large, twice as much. But that's you're stuck with tip 3P water in charm simulations. OK, so that's the strategy. So you can imagine it's very tedious. So you have to place a water. Now, in this case, we have only one hydrogen bonding group. You might have multiple hydrogen bonding groups in your drug, oxygen, another nitrogen, a couple of hydrogens. So you have to place water for each of them and then change this distance, calculate this potential using quantum mechanical calculations, and then do the fitting by modifying these charges. So that's one of the main steps that we try to semi-automate in FFTK that we will talk about later today. So they're really setting up all these Gaussian calculations, placing the water, changing its distance, getting the energies, and fitting and everything. So this is all automated in that program. So you will really appreciate that if you have done this once. So it's practically, it's difficult to do this water-based charge parameterization. But since the rest of the force field has been done that way, we have to try to stick to the protocol to be consistent. There are cases in which there is no way we can do it this way. So let's say you might have another oxygen group here, and then you want to calculate the interaction of water at this site, but then the water ends up sitting between the two like this, forming two hydrogen bonds. How you're going to separate them, and it becomes difficult. So in many cases, people might actually use a different protocol that we will talk about, Amber protocol, so to say, based on a different philosophy. But again, I mean, there is this, we all agree that we have to stick to the standard protocol as much as we can. For example, another thing that you might be able, I mean, back then they used, I think, 631G star. It's the basis set they use, and at the level of Hartree-Fock. So you might be able to do much better nowadays because the quantum mechanical calculations are much faster. You can go do DFT. You can do MP3 or higher levels of theory, but you shouldn't, because then your results are going to be inconsistent with the rest of the force field. So we have to try to stick to the standard protocol as much as we can. If you can't for practical reasons, then you write in the method section of your paper, well, for this and that reason, I know I should have done water-based, but it didn't work, and it had problems. Therefore, I decided to do my charge assignment differently. And then the reviewers are going to forgive you for what you did. You need to tell them that you know what you were, what the standard protocol is, but then you justify why you didn't follow that standard protocol. So this is one strategy. The other strategy that was followed in Amber was, OK, so instead of trying to fit the interaction to a specific molecular species, I say, and I'm going to now use this example here, the amino site. What I would like to have is, on the surface of my molecular species, or my fragment, I want to have the sort of electrostatic potential, created on the surface that is consistent with my quantum mechanically calculated electrostatic potential. So electrostatic potential is a sort of much more real thing compared to partial atomic charges. You can get that from your QM calculations. And now I want to have a set of charges at these sites that reproduce the same electrostatic potential, because that's the most important part where other species are interacting with my molecule. So if I have the same electrostatic potential here, then I will have a very good representation of my electrostatic interactions between the molecular species and everything else. So instead of doing this, they do ESP, or restrained ESP, sometimes it's called. So that too can be obtained directly from the Gaussian or other QM calculations that you can do. So this is much easier. There are problems here. You have many ways of fitting. So because it's a fitting problem, there are lots of solutions. Sometimes you get crazy solutions. Initially, if you have a buried charge, for example, you might have a negative charge for your iron in the middle of many ligands, because So there are many solutions, and there are lots of technical issues could be associated with that. So you have to keep an eye on that. But it's much easier compared to the other approach. OK, so now this was one aspect that we need to remember. The other thing that is important here is that it doesn't matter what you do, the charges are always conformation dependent. So what does that mean? That's another. So we start talking about the problems. So let me back up. So what are the problems with the assignment of a specific charge to atoms in the beginning of the simulation and continue with that fixed representation? Anybody wants to make a guess? There are many problems. I couldn't hear you. Formation? I cannot hear you guys. Polarizability, polarization, yes. So I assign 0.5 minus 0.5 charge here and 0.5 charge here. And let's say during my simulation, a sodium ion comes here. And I have a huge positive charge here. Of course, this charge is going to change, right? This is not going to be minus 0.5. It probably becomes minus 0.8 in the presence of this because it attracts a lot of electrons. Very, very important effect. We simply don't have it in our simulation. So lack of polarizability, this is a major problem. So now this is an explicit case. There are people actually working on polarizable force fields. So instead of having a single atom with a single charge that you can't do anything with, so we're going to say, let's say if instead of having my atom which has a mass of m, I'm going to take a tiny mass away from my central atom and connect a little guy to it, a sort of a fake particle to it that is a little bit separate from the position, so a little bit off center. And this guy has the residual mass on it. And now I can define a little dipole here. So instead of having the total charge here, Q, I can reduce it by a little amount of charge here and give this to the other guy. The total charge and the total mass are still the same. But now you have introduced a little dipole here that can respond to electric field in the environment. So let's say if this end is a little positive, now you have a little bit negative, a little bit positive here. When you bring the sodium ion here, for example, then this guy is going to move to that position and create a little dipole, some representation of polarization, atomic polarizability, which is what happens in your real molecular system. When the sodium is here, the electronic cloud will be drawn to this position, and then you will have more accumulation of negative charge. So this is one way of implementing some polarizability. So what are the other examples in which polarizability becomes an issue? The other example is the conformation, different conformations of your molecular system. So let's say I have something that has an oxygen here, for example, a carbonyl group here, and then I might have two hydrogens here. So this is a free bond to rotate. So these hydrogens can keep rotating here. Is this? Oh, I need another hydrogen back there. And maybe another hydrogen. So this hydrogen, if it's close to this oxygen, it can have a different charge because it's close to a negative charge. It will be more positive. Let's say it's going to be positive 0.4, for example. And if it's away from the oxygen, it can be less positive, let's say 0.3. So now in the beginning of your simulation, first of all, you want to parameterize this. So then depends on, let me use actually a different example. So hydrogens are free to rotate. I might have actually, let me put something that is, oh, let's continue with this. It doesn't matter. So So if you assign a point charge, 0.04 charge here and 0.03 charge here, then during the simulation this might rotate. Then you might end up with having the wrong charge in the wrong position by just flipping the position of these two hydrogens. So all the charges become conformation dependent. So depending on the initial conformation that you use for your drug to calculate these partial atomic charges, then your charges can be different. This is a very simple example. In this case, my solution is that I have to symmetrize all these hydrogens. That's a kind of constraint I need to include in my charge parameterization. That is also facilitated in FFTK. So you can symmetrize identical groups where you have free rotation of a bond. But in general, depending on the initial configuration that you use for your compound, let's say you might have these two conformations for your drug, right? Trans and cis conformation. If you use this conformation, you get different set of charges. If you use this configuration, we get a different set of charges. So which one are you going to use to develop your initial parameter set and then use it for the rest of your simulation? So these two tips that might be helpful. See, I mean, you might have some idea what the conformation of your ligand in your binding site is. So obviously, we want to use the same conformation to develop charges. And the second tip is, as I pointed out yesterday, if you feel that this might be really important, then you should probably try them both in different simulations. Let's have one simulation with this set of charges, another simulation with this set of charges, and see what happens. We know at least. But I mean, you see, I mean, there are lots of problems associated with lack of polarizability in the force field. And I think that's one of the largest sources or most important sources of error in these fixed charge representations that you have to use. Related to this sort of extreme example of polarization could be charge transfer or even proton transfer. So bonds are always there. So when you define a bond, it never breaks because you're using a harmonic potential for the bond, right? You can stretch the bond as long as you want. It never breaks. It just goes higher and higher in energy. So the bonds don't break. You can't have proton transfer. You can't have change in the protonation state of side chains, which is another example of not having polarization there. So there are lots of problems with the fixed charge approximation in the force field. So therefore, it's very important to do the best you can in the beginning. These are very strong interactions between the ligand and the binding pocket or whatever you are interested in that important region of your protein. So it's important to spend some time on it and do it as good as you can. Questions? Everybody clear? Good.
So you just said you cannot accommodate protonation on different groups?
So we'll get there. That's the next kind of long stretch of one of the slides. All right, so this is my potential energy function. So now I want to get all these numbers. Where are they coming from? In NAMD language or charm language. So some of these are coming from the geometry of the system. You can directly calculate them from the set of coordinates that you're working with. Most of the parameters that are specified in blue come from the parameter file. They have to come from somewhere. So now, as I discussed for the initial simulation that you set up, the geometry comes from a PDB file for your protein, usually. The charges are stored in the PSF file eventually, but coming from a topology file. When you use PSF gen to generate PSF, protein structure file, That's another thing about charm. Everything is protein-centric because initially it was developed for simulation of proteins. So everything is a residue. Everything is a protein, sort of a standard language. So use a topology to generate PSF files that contains charges. Charges are there if you want to do some crazy manipulation or modification of this. You have to work with the PSF file. We will look inside that file. And the rest of the parameters are in the parameter file. So these are the 3 files you need: a PDB, a PSF, for which you need top files, and then a parameter file. These are the 3 elements you need to start your NAMD run. Of course, you need also the NAMD configuration file, where you specify the temperature, the conditions, how long you want to go, what's the dielectric constant, is there something fixed, et cetera, et cetera. So let's look at these files. No, I need my glass. Can you guys see it from the back? OK, so I tried to increase the font as much as I could. OK. All right, so this is a parameter file. So let's just start with the PDB, which is very simple. Most of you know it already. I can make it even bigger here. So PDB is very simple, you know. Excuse me. So you have lines starting with atom or het atom. Then the index is completely useless. Nobody uses indices in PDB because it's limited, and every program defines its own indices. Then you have the atom name. So this is important now to pay attention. Atom name is just an address. It doesn't have any chemical meaning. It's just a name. You can use your own initial for the atom name when you're generating your own topology file. And then you have a residue name or res name in VMD language. When you're making selections, you say res name this, that. 3-letter code here. And then you have res ID. So this is the ID for the that's usually the original sequence number for that residue. For most proteins, it doesn't start with 1 because you don't see the beginning or the end of your protein. The crystal structure, it starts with 10 or 20 or 100, whatever. So this is the original sequence ID of this residue methionine. Each residue can have only 1 atom name of a kind. So you cannot have 2 atom names, same atom names within the same residue because there is only 1 address. This is like the street, and these are the house numbers. And now later we're going to find out how big this house is. Is it 2-story, 3-story, 1-story? The chemical nature of those atoms or addresses will be specified later. So we just know atom names, res ID, res name, res ID, x, y, z coordinates of the position of these atoms. We also have something at the end called the seg name. We use that a lot in the PSF gen. So that's this is the example of ubiquitin that you used yesterday. So seg name U is the protein itself. And there are these 2 additional columns that are B factor and occupancy that we don't use them directly for simulation. These are some information from crystallography. But we can use these columns to flag some of these atoms to be fixed, constrained. You can put even the RMSD values for these atoms here, and then ask VMD to color your molecule based on the information given in the B or in the OCC column of the protein. Yes?
Why is there no correlation with the B factor and the why are they all gone 0?
So this is, I think, in this case, this is a file generated by VMD, I think. I think these are not real in this case. Yeah. So this is a ubiquitin in a water box, I think. Yeah, ubiquitin in a water box example that you guys were supposed to work with yesterday. I don't know how many did, but so okay. So we get the coordinates, and then we get some information about the ID and the name. So everything is a residue in charm language, as we discussed. So this goes on and on. You have residue 2, 3, 4, and then we, okay. Okay. So then, so we are done with the first segment, U, and then we start with the next segment. So these are usually separate molecular species. So the next segment is the water box 1, and then you have, again, the same thing. You have one residue here, so let me see if I can. This is one water molecule composed of res name tip 3, and then we have res ID 5. Somehow we don't have 1, 2, 3, and 4. Who can tell me why? Yes? Yes, exactly. So you start with the water box. Regular water box has all the res ID 1, 2, 3, 4, 5, et cetera. And then you place the protein inside it and removed all the water molecules that were overlapping with the protein. And then because the program keeps the original sequence number of your residues, you end up having gaps. Good. But you have 3 atoms, atom names OH2, H1, H2, unique atom names within each residue, and their coordinates and the segment name. And this goes on and on. So pretty simple. So no information about the topology, connectivity. It's just a, yes? Chain. Yeah, so chain could be somewhere here, I guess. Yeah, it doesn't have to have a chain. Chain, you don't need it for NAMD PSF generation. The only thing we need is the segment name. We start a new segment, and then we put things together. We don't need to have. But sometimes you have a chain name somewhere. So there are lots of problems and lots of limitations with this file format. First of all, it's a fixed file format. You need to have these things exactly at these columns. If you go a little bit to the left, to the right, you mess it up. So if you want to modify these things, make sure that you keep it exactly at this. So like the chain is, again, I don't remember where it is. To the right? To the left. So chain name should be here. So you don't have it, fine. So it's not going to read this as the chain name. The chain name has to be on this column. It's not there, it just skips it. So if you want to modify this, and then there are limitations in terms of the number of characters you can use here. So each segment cannot have more than, I think, 9,999 residues in it. So now if you have a water box that has 100,000 water molecules, because your system is too large, then you have to break it into multiple segments. That's why we have this WT1, so we can have WT2, WT3, et cetera, et cetera. So lots of limitations. As I pointed out, the indices are very limited. For most molecular systems, they're too limited, so we have to redefine everything. But that's a standard format that has been used in structural biology for a long time. And we are sort of, we have to continue to be compatible with this format, but new file formats are coming. So we have for VMD, there are actually something called JS, standing for John Stone, who is the main developer of VMD. So these JS files, because he created them for one application, we just called them JS, and now it became the standard kind of file format name. So they can include like easily up to billions of atoms, easily. So they don't have these restrictions. So that's you start with the PDB, and now we have to sort of generate a PSF. What does a PSF mean? So PSF needs to include topology. So let's look at the standard topology file from CHARM. So this is a topology file for all atom version of protein and lipids, version 27. There are newer versions available, so this is just an example I'm showing here. Especially if you want to do lipids, you have to use 36 or later version of the force field. So bunch of headers here, and then you have the version of the topology file specified here. Alexander McCarroll, he is actually the main person who has maintained the charm force field. He has a website where most people who develop new force fields actually contribute to that website. So he is in charge of updating the force field regularly. So if you want to get the latest version, you can go to to his website at University of Maryland. So that's always a good start. Maybe somebody else has done parameterization for your drug molecule. You don't have to start from scratch. You can go there, get it from there, and then see if you like it, or you want to modify it, or you want to test it to see what happens. So OK, so this is the header. Anything with exclamation mark is a comment. So you get some information about the references and et cetera, manuscript in preparation, Scott Feller. And then you see, for example, new alkanes. They are working with the small alkane molecules, model compounds, to generate parameters that are used, for example, for lipid tails, much longer tails, but you don't have to parameterize the entire. Alkenes, things that have double bonds. Scott does a lot of lipid simulation. Yeah, here, unsaturated lipids at low hydration. They use small molecular species and model compounds to do this. OK, so but this is the actual part now. After all these comments, so you start introducing the concept of atom types. So far we had atom names in PDB, no chemical meaning, and now we start looking at atom types. Atom types have chemical meaning, are associated with parameters, masses, and so we have to introduce these different atom types. You can see a lot of H's. These are all hydrogen atom types that we use for different types of interactions between hydrogens and other species. All of them have the same mass, obviously. The mass is the same, but we have to introduce these labels for these atom types that we will use later. The same for carbon. So here, see a lot of different types of carbons, all having a mass of 12. So carbons are introduced here. Then we have nitrogens, oxygens, and then we come down here for calcium, zinc, iron, and the dummy atom here. We were talking about this dummy atom yesterday with some of you guys. So you can use this dummy atom, mass of 0. You can use it for specific purposes. Another set of hydrogens, carbons, et cetera, that are used in lipids. Again, same concept. So we introduce all these atom types and their names and masses. Then we make a few declarations here. Anything in charm can be approximated, any command in charm can be approximated to 4 letters. So decl is the short form for declare. So we are going to introduce a few new atom names because we're going to need them to connect amino acids. So like minus C alpha is the C alpha of the previous side chain, because we need to connect the bond between this side chain and the previous side chain, and define a bond angle, et cetera, et cetera. Minus C is the carbonyl carbon of the previous atom. Minus O is the oxygen of the previous residue, sorry, not atom. Plus N is the nitrogen of the next side chain, hydrogen connected to that, and the C alpha. So a few new names that don't exist in the PDB, but when you're putting amino acids together to form a peptide chain, you need to have them to define the bonds and angles. Then we make some rules. By default, the first residue in your segment is going to be patched, and we talk about these patches shortly. Will be patched by something called enter, or short form for N-terminus. Because again, everything was assumed to be a protein initially. They wanted to simulate a protein. In a segment, you have a polypeptide chain. You're going to cap the first residue with N-terminus, something special. And by default, the last residue will be patched by something called C-terminus. So I do not like this default behavior. So I will talk about this when we get to the patches. So if you want to shut down or sort of deactivate this behavior, you have to specify that somewhere. So like, for example, if you have a segment of water, it doesn't make sense to try to patch the first water molecule in your water box by this and that. So, and then by default, automatically all the angles and all the dihedral angles are generated for you. So you just have to specify bonds. That makes it much easier if you are trying to develop your own drug parameters or topology file first. So you don't have to. Bonds are easy, you just see them. This is connected to that. Bond angles and dihedral angles, there are many, many combinations. It's more tedious to specify all of them. So now then you make all this sort of preamble part, and now you're ready to talk about your residues. So first residue alanine, again, residue alanine, the total charge of the residue is 0. I'll come back to this group later. So then you have these atoms in alanine. They have the atom name. This should match what you have in your PDB. That's the atom name. That's the house address. And then you specify an atom type to it. So the nitrogen in alanine, which is also drawn here for you, has an atom type NH1 and has a partial atomic charge of minus 0.47. Hydrogen connected to it is called HN. That's the name. But its atom type is H, which is usually polar hydrogen, forming hydrogen bonds. It carries a positive charge, significant positive charge here, and so on and so forth. So you specify atom types and charges for all of your atoms within that residue. So then you say, OK, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 houses in this street. These are the types of houses we have, and these are the charges we have for them. So now we want to talk about the connectivity between them. So we come down here, and you specify the bonds. OK, well, CB is connected to CA, N is connected to HN, and you go on and on. You might have multiple pairs. There is no fixed format here, so you can have as many pairs as you want. It's a good idea not to have too long lines, because then it's not readable. So you specify these bonds. Now you can see actually how we are using the plus N atom name that we created, because carbon in this residue is also connected to the nitrogen of the next residue in the polypeptide chain. So there is a bond there. So that's how we are going to use that. We only connect to the next residue. If every residue is connected to the next residue, we are all set. You don't have to do it twice, right? Otherwise, you will have 2 bonds. OK, so the bonds are defined here. So there is this back compatible kind of command here, double. There used to be a sort of explicit term for double bonds or explicit treatment for double bonds. You have a double bond here, but right now it has exactly the same function as bond. You just say there is a bond between the two, and the nature of the bond, how it should behave, only comes from the parameters. Higher force constant, shorter bond length gives you the double bond behavior you need. That's all. So it's just there for compatibility. So now bonds, we define the atoms, we define the bonds. Dihedrals and angles are generated automatically based on these bonds you define. The program goes through the system and generates all the possible angles, all the possible dihedral angles. So that means, for example, this bond will be affected by 3 atoms connected here and 3 atoms. 3 by 3, 9 different dihedral bonds, dihedral angles, coming from here, going there, coming from here, going there, coming from here, going there, and so on and so forth. So there are multiple definitions for the same bond. The rotation of this bond is affected by 9 terms in my potential energy function. So I have to distribute the barrier among all these 9 terms to get the correct barrier. So they will all be generated automatically. Bonds, angles, bonds are here, angles, dihedrals, automatic. And now I have to define any improper angle that I would like to have. So you remember impropers are formed by 4 atoms, usually working at the center. So usually we have the center atom here, and the 3 atoms connected to it are specified later. So like the first one seems to be nitrogen, and then the 3 atoms connected to it is the carbon of the previous side chain, C alpha of the same side chain, and HN of the same side chain. So this nitrogen has a partial double bond through this peptide bond, right, connected to the carbonyl next door. So this, the nature of the partial double bond gives it and partial sp2 kind of planar center. And that's what we introduce here. So later in the parameter file, we tell the program if you have these 4 atom types, because now we know the nitrogen has what atom type, the carbon has this atom type, Ca has this atom type, etc. etc. So if you have this 4 set, the set of 4 atom types that are specified here, here is the improper potential that you need to use. So that's one center, and the other center is this guy here, this carbon, and again connected to C alpha, nitrogen of the next residue, and the oxygen of the same residue. Again, another sp2 center. So we are done. So donor acceptor, again, they are there for compatibility. They are not used. We don't have explicit hydrogen bond terms in the current version of CHARM. So the way hydrogen bonds are reproduced is by having polar hydrogens. For example, you see this hydrogen has a significant positive charge on it, this guy. And if it happens to be next to a negative charge like this oxygen, minus 0.51 is a significant amount of negative charge. If this oxygen sees this positive hydrogen, they start attracting each other, and that gives you the hydrogen bond. There will be also a little bit dipole here, the carbonyl, you know, plus, minus. You have a strong dipole here. You have also a strong dipole here. The 2 dipoles also align a little bit to give you a little bit of the geometry of your hydrogen bond. That's all we have for hydrogen bond representation. So by this point, actually, you're done. So if you want to define your own residue, your own drug, your own cofactor, you're done by here. The rest is that looks very intimidating, is a bunch of IC or internal coordinate kind of information. We call it the IC table here. And the format here is in a way that allows you to guess or to determine the position of atoms that, for which you don't have coordinates. So here the format is the following. So you specify 4 atoms, and then there are 5 numbers following these 4 atoms. So these are the atom names. And then you say the first would be the standard distance between the first 2 atoms. This second number is the standard bond angle formed by the first 3 atoms. The one in the middle, the third value, is the dihedral angle or improper dihedral angle, if you have this star here, formed by these 4 atoms. Then the second last number would be the angle formed by the last 3 atoms and the bond distance between the last 2 atoms. So you can see by the very compact format, you have 4 atoms and 5 values allowing you to build the position of missing atoms in your. So if you have the position of all of your atoms, you created it in a molecular builder program for your drug, you don't need this. You can completely skip this. So now a couple of comments here. So one is about this group. Let me go back here. So again, we talked about cutoff and the fact that you don't want to calculate all the pairs because that becomes very expensive. So what we do for van der Waals interaction, that's easy. So you just cut it off at some point. But if you do this for charge interaction, so let's say you have a center here. So let's say it has a positive charge here. And then I define a cutoff. So now let's say every atom that is included in the cutoff distance will interact. I calculate the electrostatic interactions. Every atom that is outside the cutoff will be excluded. But what if I have a little dipole here? So let's say I have a dipole. Let's say I have a carbonyl group here. So now this, at the long distance of 10 or 12 angstrom, this is a dipole. So interaction is 1 over r squared. But now if you apply this cutoff, let's say this was what? Carbonyl group, this guy. So negative 0.51, and then you have positive 0.51. So at that long distance, what you feel here is just the effect of a dipole, that you have a little bit positive charge, negative charge, canceling each other almost. Whereas now if I apply the cutoff, include only this, I will have a monopole, which is much stronger in terms of interaction with this center. So you're introducing an artificial interaction. So in order to avoid that, I say, OK, hey, wait a minute. So I'm going to define this group as a charge group. So now if one of the atoms is included in the cutoff, the program has to include the entire charge group. So that's what we have here. So you define this charge group and say C and O should be always together. If they are in, both of them should be in. The same here. And if you look at the net charge, or the sum of the charges within each charge group, you can see they are neutral most of the time, or you have a net charge of +1 or -1 or things of that sort. So that's the definition of the charge group. In NAMD, by default, the entire residue is included in one group. Either the whole residue will be included in the calculation of electrostatics or nothing. So you don't really use this, but you can turn this feature on. And this was originally done to make the calculations as cheap as possible, because electrostatic calculation, non-bonded part of the calculation was the sort of the slowest part, the most expensive part, and people tried to do tricks to make it as cheap as possible. So really, so let's include only this group and maybe the other group, but not the middle part. That would have sort of saved us some computational time. But nowadays, it's so easy and so cheap, it has been sort of improved significantly. People don't worry about this anymore. So we can do residue base, but again, if for some reason you have, let's say you have a very long drug, and you would like to break it into a few groups, then you can use this trick to make your calculation faster. OK, so that was alanine, sort of very basic side chain. And now let's look at the longest side chain we have, arginine. And then we can have a break after this. So arginine residue, arginine, that's the res name, should match what you have in the PDB. Otherwise, you have to do something about that. Has a total charge of +1. Then you can see these charge groups, atom names, atom types, and the charge assigned to them. So here is the structure of arginine in case you don't remember the atom names. The atom names are not too bad. You know, you have C alpha, and the hydrogen connected to it is HA, H alpha, C beta, HB1, HB2, C gamma, C delta, N eta, zeta, et cetera, et cetera. So that might help you remember the atom names a little bit if you want to. So there is a positive charge in arginine. Arginine is basic side chain, has a very high pKa and stay protonated almost at every pH. So unless it's in a very unique electrostatic environment in the protein, and we will talk about this and protonation states after the break. So we have the same thing. So the backbone is essentially the same for all the side chains. We group these 4 atoms together in one charge group. Then we go through the side chain. C beta unit, C gamma unit is separate, and then starting from C delta, because these nitrogens are sharing a positive charge, we put this entire piece at the end in one charge group, starting with C delta, going all the way to all the hydrogens at the end. Carbonyl is interesting. The atom names and atom types are the same kind of symbols and the charge there. Then you have the bonds. All the bonds are specified here the same way we discussed. It is connected to the next residue. That gives you your peptide bond, and double doesn't have any specific function. It's the same as bond. And now in this case, in addition to the two sp2 centers in your backbone, for which you define the improper angle, you also have an sp2 center in the guanidinium group of the side chain. This guy here is also planar center, C zeta. So you define this additional planar center for which you have an improper to keep it planar. Ignoring this completely and the long IC table, you don't have to worry about. Okay, so now after the break, we're going to look at actually a few other special side chains talking about protonation state and PK assignment, which is an important step you need to do. And then some tricks you have to do for histidine, because there is no histidine name in the topology file. And then we look at patch residues, or PRES, or patches. Any questions? Yes, James. I cannot hear about it. Can you speak up?
When you have a residue like arginine that has multiple residues, the IC line is that for the reverse parameter.
So there is no, there is no conformational information here. The same Rodomer. For this you mean?
Yeah.
Oh, yeah. So this is, this is a standard textbook conformation, perfect trans extended conformation of the side chain. So that's all they have here. So this, it just allows you to quickly build a sort of going out. It might even clash to other residues. It doesn't have any notion of, oh, you should check something. It just builds something standard, like when you draw it on the board. That's the idea. No. So this one, yeah, that's the idea. And again, I think, many of the structure builders now do these things automatically, You can guess the position of hydrogens easily. So, yeah, originally it was very useful. People who didn't have all these utilities, they needed to create the position of these things. But nowadays it doesn't have much function, actually. Yes?
So did you say that for NAMD, it does or it doesn't?
Oh, NAMD works, it doesn't work with group-based charge definition, that is here. It works on a residue-based kind of method. Even if you have one atom from the residue, from your residue, entire residue included in the cutoff, the entire residue will be included in your electrostatic calculation. So that's the default behavior. You can change it by a command. Say, I don't know the syntax of the command line, but there is a command to make it use these group definitions. Okay, 15 minutes. Back in